Hello, good day. We are team number 3, and during this presentation, we're going to be talking about human detection in surveillance images from security videos. Our project focuses on developing an algorithm designed to detect the presence of humans in images from security cameras footage, acknowledging the importance of this capability across fields in computer vision, security, and surveillance. Our collaboration efforts aim to deliver a solution that can identify human subjects within images with accuracy. The three models that we evaluated were AlexNet, BGG16, and ResNet50, and we also used CV2 for object and pose detection. The dataset downloaded from kaggle.com included a diverse collection of CCTV footage images, indoor and outdoor environments. These images were grouped in two directories for two classes, allowing us to easily differentiate between images containing human subjects and those that do not. We can see that the class 1 with humans had more images than class 0 without. So during the pre-processing, we have to correct mislabeled images that we found in some of those two directories. Also, we did balance the data set by augmenting the minority class. We can see the final result here. We applied data augmentation like rotation, shift, shear, zoom, flipping. We normalized the images with pixel values to 0 and 1s, and we mapped the normalization layer to all data sets. That is test, validation, and training.
And I'll be talking a little bit about AlexNet and how we implemented it in this project. AlexNet was a revolutionary step in deep learning for image classification and serves as the backbone of our human detection project. Its robust architecture makes it well suited for binary classification of surveillance images, which allows it to handle variability in lighting, angles, and backgrounds effectively. The training process for AlexNet began with preprocessing, where images were resized to 22.7 by 22.7 and normalized for faster convergence. To enhance the dataset and reduce overfitting, data augmentation techniques such as rotation, zooming, and flipping were applied. This architecture featured 5 convolutional layers with dropout, ensuring robust feature extraction. We also use the Atom optimizer with the learning rate of 0.0001 and binary cross entropy laws to guide the model's learning. The model achieved a training accuracy of 71.45% and a test accuracy of 72.97%. Evaluation metrics, including precision at 0.71, recall at 0.74, and the F1 score of 0.72, highlighted the model's effectiveness. Additionally, the ROCA-UC score of 0.82 demonstrated its ability to differentiate between classes with high reliability. Throughout training, accuracies for both training and validation improved steadily, reflecting the model's ability to generalize effectively. Validation accuracy closely matched test accuracy, confirming good generalization. Loss metrics consistently decreased, indicating effective learning. These trends underscores AlexNet's strong ability to differentiate between images containing humans and those without. While AlexNet provided a solid foundation, there are opportunities for improvement, exploring advanced architectures like ResNet, which we did later on, or Inception, leveraging transfer learning from pre-trained models and increasing data set diversity throughout enhanced augmentation techniques, which are promising directions. These enhancements could establish a more robust baseline for future exploration in human detection tasks.
Hello, my name is Chris Aline, and I will be discussing the secondary model for this PowerPoint, which is ResNet50. ResNet 50 uses advanced architecture that's intended for feature extraction. It uses a deep feature connection with 50 layers within its CNN, hence the 50 in ResNet 50. It also uses residual connections, which are better for vanishing gradients, and that's a major issue in other CNNs. And the last reason to use ResNet 50 was the scalability, which I will talk about later in the conclusion. On the next slide, you'll see the methodology. We used our new annotated data set with the key points labeled. So in the model, you will see an outline of the skeletal system. It kind of looks like a stick figurine. We resized and normalized all of the images to 224 by 224 pixels, and that is able to most efficiently feed the images through the 50 layers of ResNet. On the next slide, you'll see the code for this architecture. So this is essentially the crux, and it produces a pretty sleek result for single-person still images, which you will see on the next slide. And these are the results. So the model is generalized well to unseen data. It is able to predict the pose very well, and as you see the layering over the initial data set, these new stick figurines or skeletal outlines are just some of the tools that ResNet 50 has in its arsenal. So the discussion, while ResNet 50 was able to extract the pose due to its pre-trained layers, feeding it through all 50, it would have a little bit of an issue currently, as is with real-time video footage. So that would kind of be the next step for our project if we wanted to take this into this AI company or a data company. We could bring this into video footage and have it track people in real time. Not just one person from still image, but also multiple people from video footage as well.
BGG16 is a widely recognized convolutional neural network architecture developed by the Visual Geometry Group at the University of Oxford. It's known for its simple yet powerful architecture. The architecture consists of 16 layers, including 13 convolutional layers and 3 fully connected layers. The model uses a 3x3 convolutional filters throughout the network, and it increases the depth by stacking multiple convolution layers to enhance feature extraction. For applications, it's widely used in tasks like image classification, object detection, and image segmentation. Even if it's known to be simple to implement, it requires higher computing resources in compared to other modern architectures. For our project, we implemented the pre-trained BGG16 from the Keras library, keeping the pre-trained weights, as we can see here in this code. Also, the image size was set to 224 by 3, set to match BGG16 expected input size. It is important to point that only the last full layers of the BGG16 base model are unfrozen and set as trainable, while earlier layers remain frozen to retain pre-trained features. The dropout was set to 50% to reduce overfitting. One of the critical arguments we found to increase the training and test accuracy was the atom optimizer with a learning rate of 1e6. With a small learning rate like this one, the model makes tiny updates to its weights in each step, which can prevent overshooting the optimal solution and ensure more precise convergence. Like in our application, this value is typically used when fine-tuning pre-trained models to avoid disrupting already learned features. The final results shows a discrepancy between the training test accuracy and the classification performance metrics. While the model achieved a high training accuracy of 90% and a test accuracy of 92%, the classification report shows a poor performance with the overall F1 score of 58%, low precision and recall for both classes. Some of the potential issues could be overfitting, where the model performs well on the training and test sets, but fails to generalize a broader, more diverse data. Also, despite augmentation, the model may still favor one class, as indicated by the imbalanced precision and recall classes of 0 and 1. This tells us accuracy alone does not reflect the true performance when dealing with imbalanced or nuanced datasets. Precision recall and F1 scores highlight the model's inability to effectively distinguish between these two classes. Further investigations, such as refining the dataset, adjust thresholds, or employing advanced techniques like weighted loss functions, is needed to improve the generalization and classification performance of BGG2. For reference, this image was classified properly by BGG16 and then used CV2 to do object detection. On the image below, the image was misclassified as the humans are behind branches of the tree and the model could not properly classify it.
To wrap up, we explored 3 powerful CNN architectures in this project. Firstly, we explored AlexNet, followed by BGG16 and ResNet 50. While AlexNet laid the groundwork with a strong baseline, offering reliable accuracy and good generalization, BGG16 took it further with more detailed feature extraction and higher accuracy, though it required more computational resources. And finally, ResNet 50 demonstrated advanced capabilities in pose estimation, effectively handling diverse poses and complex scenarios. Looking ahead, there are exciting opportunities to explore advanced architectures, leverage transfer learning, and also enhance dataset diversity with more sophisticated augmentation techniques. Additionally, integrating real-time capabilities and multi-person detection will open up new possibilities for broader applications. These models together set the stage for future innovations in human detection and post-analysis systems.